Now, the type of problems that we really want to solve look like this. Sketch a graph of, and then they just give you some function. And you got to figure out all sorts of stuff. Okay. But I decided to do things a little bit differently. What we're going to do first is we're going to do everything backwards. In other words, we're going to start knowing the graph, and then we're going to pick out all the pieces. And then I figured after doing that, then we can do the reverse, which is you don't know what the graph looks like, but you can find all the pieces, and then we're going to learn how to put all the pieces together. That's going to be our goal. Okay. So let's take a look at this warm-up here. The first question they ask is, what are the intercepts? Now, there's two types of intercepts. There's X-intercepts. And to find the X-intercepts, you got to set the Y coordinate equal to 0 and solve for X. Okay. For the Y-intercept, it's very similar. It's kind of just the opposite. So for the Y-intercepts, what we're going to do is we're going to set X equal to 0, and then you solve for what Y is. Okay. Now we're just looking at this graph here. So when I look at the X-intercepts for this graph, I can see there's one right there and there's one right there. So if I were to write down what those were, I would say X equal to 1.6 and X equal to 3.8. I just made up those numbers. I'm estimating. I can't really calculate it. I'm just looking at the picture. Is there any questions about them? The Y-intercept is right here. So the way I'd find that is I'd set X equal to 0, it's solved for Y. It looks like Y is equal to 10. Okay. So whenever we do curve sketching, we generally want certain points to anchor our graph. So what would the anchoring points be? Well, one anchoring point you get is you get the intercepts right here. These are like anchoring points as the intercepts. The other sort of anchoring points that we generally calculate are inflection points and local maximums and minimums. Okay, those points will anchor our graph. Whoops. We also want to create like a framework or have a rough idea of what our graph looks like. So we wanted to know what the end behavior is. And the end behavior is the behavior at infinity. So all the way out here and all the way out here. And when I look at this picture, it looks like this graph is going up and this graph is also going up. So I'm going to write as x goes to positive infinity, our graph f of x goes to positive infinity as well because it's going up. If it went down, we'd say negative infinity. If it approaches the horizontal asymptote, we'd say y equal to whatever that horizontal asymptote is. For this guy as well, as x goes to negative infinity, f of x goes to positive infinity, because even though we're going to the left, our function's still going up. Is there any questions about the end behavior? Okay. So if I told you that this graph was like y equal to x to some power, what could you tell me about this power? Can anyone unmute themselves and tell me, or type their answer in the chat box? Or what can you tell me about this power, knowing that this is true? Any thoughts?
It's even.
That's right, because even powers go like this. If there's a negative coefficient in front, then the even powers would go like that. But it's the odd powers that are the other direction, like this and like this. Okay. Okay. Next, we wanted to figure out what are the intervals of increase and decrease. So I'm going to do two things. I am going to both draw a little number line and also use interval notation. I haven't been making a big deal about the interval notation, but I'm going to now. Okay. So I could just give you the straight answer. I mean, just looking at this graph, it kind of decreases to whatever this point is, and then it seems to increase here, right? And when I look at it with that x value, the x value is over equal to 3. So I could easily put a 3 here like this, and then go like this, and then like this. And that would be correct. But I'm going to put one extra point right here. And that extra point I'm going to put is 0. Now, why am I putting 0? It's not because it's 0. It's because when I look at this guy, can you guys imagine that I have a horizontal tangent line right here? Like it sort of flattens out for a split second and it goes from negative, and then it continues to be negative. So really, I think my picture kind of looks like this. But my answer is just going to be from negative infinity to 3. That's where it's decreasing. Where is it increasing? From 3 to positive infinity, it's increasing. And where's my local maximums and minimums? I think we can all see that you have a minimum here at 3. Is there any questions about this? Okay. Then the final thing we want to do is we want to find intervals of concavity. So I feel like this is a little bit harder as far as looking at the picture goes. We're going to need to estimate. I want to label all the points where I think the concavity changes. So we're really estimating here, okay? Like you don't know for sure, but I'm pretty confident that the concavity changes at 0 here. Because it looks to me like it's concave up here, and then it switches to concave down at 0, right? So I'm going to come over here. I'm going to put a 0. It was concave up here and then concave down here like this. And then where's the next point where it looks like it switches concavity? Well, it's concave down here, and then along the way it switches to concave up at some point. It's really hard to see where that point is. I'm just going to pretend like it happens at 2. To me, it looks like, oh, it could be concave down here, and then it flips to concave up from here. If you said it was at 1.8, I can't tell just by looking at the graph. We have to do some calculations. But certainly I wouldn't mark that wrong. I'm not going to ask you to do the warm-up. I'm going to ask you to do the reverse. So I think once you hit 2, it becomes concave up like this. So the way that we write this in interval notation is we say it's concave up from negative infinity to 0, union 2 to positive infinity. That captures both of these intervals here. And when is it concave down? It's concave down. Oh my God. Concave down from 0 to 2. Does that make sense? Is there any questions? So I was trying to explain to you guys a little bit last time. We can take this increasing, decreasing information combined with the concavity to draw a series of like curved arrows that will help us understand what the graph kind of looks like. So if I were to, maybe I'll use a different color, I'll use green. If I were to look at something that was decreasing but concave up, I think I would write it like this. And then if it was decreasing and concave down, I think I would write it like this. Oops. Shoot, I drew this way too big. And then if it's now increasing, oh, I messed up, sorry. I don't have enough room here. Let me start over. Part of the problem is I want to reproduce my graph so that it kind of is all in the same number line here. So let me put the 0 here. Let me put the 2 here. Let me put the 3 here. Okay. And then I'll just reproduce this. So from the left side of 0, it's decreasing. Between 0 and 2, it's still decreasing. Between 2 and 3, it's still decreasing. But from 3 on, it increases like this. So once we have this information, if we want to piece it together, how does it look? It's concave up and decreasing, so it looks like that. Then it's concave down and decreasing, so it looks like this. Then it's concave up and increasing, so it looks like this. Then we have a local minimum here. This is a min. And then it's concave up and increasing, so it looks like this. So can you guys see how when I join these pieces of information and then I connect each of those segments, I get something that looks kind of like my graph. I mean, if I had it on a real number line, it would look pretty close, I think. So that's kind of what we're trying to do. Did anybody have any questions about this warm up before we play detective and try to piece together the graph of a function that has many pieces?
I have a question. How did you know to use 2 for the intervals of concavity?
How did I know?
To use 2 as a point?
I guessed. You see this part, it says you need to estimate.
Oh, okay.
Like I was trying to say, is it here? Is it here? It's like somewhere in here, it switches concavity. I'm not really sure where. But when we, oh my God. When we put ours together, we're going to actually have numbers. So we won't be looking at a graph. We'll be trying to create the graph.
Okay, thank you.